How's it going, ladies and gentlemen? Mr. Ronnie here again, taking a look at 16.6. Here are the objectives. Things you want to be able to do. Feel free to pause it, read through them, come back to them at the end of the video, see how you feel about each one of them. All right, let's get started. 16.6, number 1. An aqueous solution of HZ, which is a weak acid, is prepared by dissolving 0.04 moles of HZ in sufficient water to yield 2 liters of solution. The pH of the solution was 4.93 at about room temperature, 25 Celsius. What is the Ka? All right, first thing that we need to do is we need to go, hey, wait a minute, 2 liters of solution, they're not being nice with this problem. If I'm going to be dealing with molarities and they give me moles and liters, it would have been nice if they gave me 1 liter, but they didn't. They gave me 2, so I got to convert this. All right, well, what is the molarity of HC? Well, it's not incredibly difficult math, but if you forget to do it, it screws everything up. So you get 0.040 divided by 2 liters, and you get 0.020 molar. So that is the concentration of HC. All right, it says, pH solution is this. All right, well, let's figure out first what the Ka expression should be. So the Ka should be the concentration of H plus times the concentration of Zn minus all over the concentration of Hz. Can't draw Z's today, at equilibrium. Now, that is just, this is the equilibrium. Just, where did that come from, Donnie? I got no idea. Well, it's just, all right, well, it's going to break apart into this. So equilibrium expression constant right there. So they tell me the pH, which helps me because that can help me figure out, well, what's the concentration of H plus, which is going to be the same concentration as Zn minus. So next step I got to do is, all right, well, I know the pH equals negative log of the H plus concentration. So I need to solve for H plus, so I rearrange things. I move the negative to the other side. I get rid of the log by putting everything on that side to base power, 10 to the negative pH equals concentration of H plus. They gave me the pH, now it's just plug and chug. So what do I get when I do that? 1.17 times 10 to the minus 5. And that is molar for the H plus. All right, well, let's think about this. What's gonna happen? Well, so I plug in my Ka. Well, that's going to be 1.17 times 10 to the minus 5 times the same thing again. So I'm just going to square it, all right, because the H plus is the same thing as the Zn minus. And I don't feel like rewriting that whole number. All over the concentration that we started with, which was 0.020, but then we have to subtract how much was used up. Right? So if that's the molarity that I started with, it's not molarity that I had at equilibrium. Some of it became the H plus and Zn minus. How much? That much. So we do minus the 1.17 times 10 to the minus 5. And we get our final answer being 6.91 times 10 to minus 9 as our final answer. All right? So, yeah. That's all that really is. All right. Number 2. In which of the following aqueous solutions does the weak acid exhibit the lowest percent ionization? All right, so we can figure this out indirectly. So lowest percent ionization, well, we also remember Ka is essentially the products over the reactants. And if we're talking about the weakest acid, the one that ionizes the least, well, we want the smallest Ka. So we can look at this. We got 10 to the minus 5, minus 4, minus 4, minus 8, just to quick eliminate some things. All right, well, the ones that we can eliminate are the bigger ones. Now, again, don't get tripped up here. It's scientific notation. These are negative exponents. So the smaller the negative, the bigger the number is. So it gets rid of B and C, and also A. It leaves us with 1. Choice D, as in David. That one has the smallest Ka, so it's going to ionize the least. Trace. The pH of a 0.6 molar aqueous solution of formic acid, given by the formula here, at 25 degrees Celsius is 1.98. What is value Ka for formic acid? All right, so let's figure some of this out. So first thing that we're going to do is we're going to have to use the Ka to figure out H plus and stuff. All right, so we know the pH is 1.98. So let's do a little math. Well, I know if pH equals 1.98, that also equals the negative log of the H plus concentration. So I gotta get H plus by itself. So I get 10 to the negative pH equals the concentration of H plus. pH is 1.98. I plug that in, and I get my number, which is 1.05 times 10 to the minus 2. So that's my molar concentration for H plus. All right, so let me figure out the Ka. Ka expression should be H plus times by, CHO2 minus all over the undissociated, the stuff that didn't break apart, HCHO2. All right, well, I just found my H plus, which is going to be equal to the CH2, or I'm sorry, CHOH2 as well. So I'm going to, it's going to be 1.05 times 10 to the minus 2 squared. I'm not going to rewrite it twice because these two things are equal to each other. Same thing as squaring that number all over the concentration that I started with, which was 0.60 molar, minus the amount that dissociated, which was 1.05 times 10 to the minus 2. Right? Because I just found that here. That's how much broke apart to become H plus and CHO2 minus. So I know that I don't have 0.6 molar anymore because I lost some of it. So now I just plug and chug. Use a calculator, and you get 1.87 times 10 to the minus 4 as my Ka. So that's my final answer. 4. What is the pH at 25 degrees Celsius of 0.0200 molar hypochlorous acid given by that formula solution? And they give you the Ka. So first thing that we're going to have to do here, we're going to have to go, all right, well, Ka, give me my H plus. And then from there, once I got the H plus, I can go H plus to what's my pH. All right, well, let's set it up. I got my Ka is going to equal the H plus concentration times the ClO minus concentration all over the HClO concentration. All right, well, let's figure this out. All right, so we're going to have X amount of H plus. We're going to have an equal amount of ClO minus all over, well, we started with 0.200 molar minus the amount that dissociated. Right? How do you get that? Well, I could set up an icebox thing, which I'll do it. So I started with HClO, and it broke apart to become H plus and ClO minus. Well, initially I started with 0.0200 molar HClO. I had no H plus, and I had no ClO minus. Then the change. Well, I don't know how much it is, so I'm going to call it X. I used up X amount. I made X amount of H plus, and I made X amount of ClO minus. So at equilibrium, I'm going to have 0.0200 minus X. I'm going to have plus X, and I'm going to have plus X. So that's how I got those numbers up here. All right, now I need some room for work, so I'm going to erase. All right, so now how am I going to do this? How am I going to use this information to solve for X? You're going to distribute. You're going to get like a quadratic equation. You're going to use that to solve for X. So when I do all this out and combine like terms, I'm going to cheat a little bit. I'm going to get X squared plus Ka times X minus 0.0200 Ka. How did that happen? Well, I multiplied everything by the 0.200 molar minus X to the other side, Ka, so I distributed the Ka there, and then I got everything on the same side. So I get 0 equals this. So now, going back to, trig, where you get X equals, negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is 1 B is our Ka, and C is the product of 0.0200 times Ka. So now it's just plug and chug. You're going to get two answers. Only one X makes sense. It's going to be usually it's the positive value, because if your change is, you can't have a negative concentration, right? So we solve for X. I lost my spot. We get X equals 2.45 times 10 to the minus 5. We're done, right? Nope. All right, we're halfway there. This is X, which is the H plus concentration, but they're not asking for that. They're asking for pH, right? We just finished that first step. So now we can do step 2, where pH equals the negative log of that number, 2.45 times 10 to the minus 5. And we plug and chug, and we get 4.61 as our final answer. So to review here, we had to start, use Ka to solve for X. H plus concentration, use the quadratic equation, and then the second step, easy step to forget to plug in, get the final answer. Bada bing, bada boom. All right, 5. It says the acid dissociation constant for sulfuric acid given by that formula are, so they give you the two different, right? Why are there two different ones? Because it's a diprotic acid. It can give off two different H pluses. Calculate the pH of a 0.163 molar aqueous solution of sulfuric acid. All right, so I'm going to cheat a little bit. So I'm looking at these numbers here, and I got 1.7 times 10 to the minus 2, and then the next number is 10 to the minus 8. So there's a huge difference, right? Like, that's a million times difference in those Kas. That's a million times difference in those Kas, which means most of my H plus is going to come from that first dissociation. That first H plus is going to come off. The next one's going to come off, but not nearly to the same degree as the first one. So I can cheat and just look at the first one. So it wants a pH, which means, all right, well, I'm going to have to get the H plus concentration. How am I going to do that? Well, my first trick is I'm going to use Ka to get my H plus like I did in the last problem. Right? All right, then what's my second step going to be? Well, what are they actually asking for? pH. So then you use the H plus to give you the pH. So let's do a little bit. All right, so I get my Ka expression to equal the H plus times the HSO3 minus all over the H2SO3 concentration. All right, well, how much H plus and HSO3 am I going to get? I'm going to get X amount of each, right? All right, well, how much H2SO3 is going to be left over? Well, I started with 1.63 molar, but then I used up X amount that dissociated. So now I'm going to, combine all these like terms. All right, I'll work out the algebra on this one. I get X squared equals, well, I got to get rid of this denominator, so I times both sides by that. Ka times 1.63 minus X. Let me distribute that Ka. I get Ka times 1.63 minus Ka times X. That equals X squared. So now let me get everything on the same side. So I get X squared plus Kax minus the Ka times 1.63, and that's going to all equal 0. So now I got my Ax squared plus Bx minus C set up, where I can use that quadratic equation where x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm going to get one x value that makes sense. All right, so I plug and chug, and I get 4.48 times 10 to the minus 2, and that is my molar concentration of H plus. Done? Say no. No. All right, good answer. All right, we just finished that first step. We got our H plus concentration. Now we got to plug it in to the pH equation, where pH equals negative log of the H plus concentration, which was 4.48 times 10 to the minus 2, and we get 1.35. That's it. All right, you could keep going. You go, all right, well, if this is how much H plus I got, I know that's all. Well, that's also how much HSO3 I have, and then let me do the Ka2 as well. Same step to figure out how much additional H plus I would get. But when you compare it to 10 to the minus 2, you'll see that it's a drop in a bucket. You know, so you can ignore it and still get essentially the same answer of 1.35. All right, so number 6 is a tough one. It says we got a solution of acetic acid that's 2% dissociated at 25 degrees Celsius and wants the original concentration of the acetic acid in solution. They give you the Ka. So let's start with the two general equations that we got. We know Ka is going to be equal to H plus times the anion all over the original, how much is left, right? So if we were to rewrite this in terms of X, all right, well, we don't know how much H plus we got, so it's X times, well, we got the same amount of anion all over the initial molarity minus the amount that dissociated. So that is our Ka expression using X as a variable for how much H plus there is, and M1, the original concentration. All right, well, that doesn't help us a whole lot. So what's the formula for percent? Well, the percent is going to equal just the part over the whole, right? So, well, the part that we got is we don't know how much H plus we actually have. So let's just call that X again, all over. Well, how much X is the percent, right? No, let me just. All right, so we know that the percent formula is the part over the whole times 100, right? So the part that dissociated is X. We don't know exactly how much. The whole thing is how much we started with, which was our original molarity, times 100, which we do know that has to equal 2%, right? So we have these two equations here. We got two unknowns, so what we can do is we can combine these two equations so that we have one equation with one unknown. So what I would suggest doing is to go, all right, what are we trying to solve for? The original concentration, M1, right? So let's plug things in. Let's solve for X in terms of M1. So let me look at this percentage equation. Let me get M1 by itself. In order to do that, I got to multiply. It's just algebra. I'm not going to bore you guys with it. X equals the original molarity times 2.0 over 100. So now I have an equation for X that I can plug in to this equation to get me a third equation with only one unknown. So now I got Ka equals, well, X, again, I said, is M1 times 2 over 100. And that's essentially going to be squared because it's X times X. So I'm just going to put squared there. All over M1 minus X, which was M1 times 2 over 100. And now I have one equation, one unknown, because Ka was given to me. So now I'm going to plug those things in. I'm going to distribute, right? I'm essentially going to get 0.0004 M1 squared all over 0.98 M1. Now watch what happens. If I got M1 squared on top and M1 on the bottom, I'm left with this, 0.004 times M1 all over 0.98 has to equal to Ka. So now I get M1 by itself, right? So it's Ka times 0.98 divided by 0.0004 equals M1, and I plug and chug, and I get 0.0441 molar as my final answer. So the hard part here was realizing you had to combine those two formulas to give you one formula with one unknown. Alright, so that, yeah, that's the tough part. Alright, then we take a look at number 7. A solution of formic acid is 3% dissociated. What is the original concentration in molar of the formic acid solution? So this is just like the last one. So hopefully I can do a better job of explaining this one. So again, I'm going to jump the gun a little bit. Ka is going to equal an unknown amount of H plus times an equal unknown amount of the anion all over the original concentration minus the amount that dissociated. Alright, so I hope we're good with that so far. We started with some amount, we don't know. Certain amount was used up to make the same amount of H plus and its anion. So that's my Ka expression. Now my percent, well, that's 3%, has to equal that unknown amount of H plus all over the amount that we started with times 100. Right, so now I'm going to try and rearrange this so that I can get like, x and substitute x in for something that's got m1 in it. So I got to do, a little algebra, but it's just algebra. I can divide each side by 100, so it's 3 over 100, and then I times each side by m1, and that gives me an equation for x. So now I have these two equations, two unknowns. Now I'm going to plug one into the other. I personally think it's easiest if I plug this one into that one. So now you get Ka equals m1 times 3 over 100 squared, right? That's the top right here, all over the amount that I started with minus x. And again, x is m1 times 3 over 100. Now, let me combine like terms. All right, so this bottom one is just going to be 0.7 of my original concentration. I'm sorry, 0.97 of my original concentration. And what's going to happen when I have 0.3 m1 squared up top? I'm going to get 0.0009 m1 squared. Well, I got m1 squared divided by m1, so I'm going to get m1 the first power up top. Now these are just numbers, right? So now I just got to get m1 by itself. So I got to do a little more algebra. I get 0.97 times the Ka, gets rid of that denominator, divided by the 0.009, gives me m1, which equals 0.194. Again, the last two were tough problems because you had to combine two formulas to give you one, which is not something you do a lot in, math or science at this point. Probably haven't done a whole lot of it. So don't let it freak you out. Just think about what's going on. All right. Well, and then beep bop boop. Get your answers. Bring questions. I'll work through these in class if you need me to without any